All right. To uh, speed up the learning process, I decided to record a video, and I will upload this to YouTube. Then later you can watch and hopefully learn. So this is the address of my GitHub repository at github.com/simsecergon slash like there are a bunch of folders. The one today I will be talking about is Waveguide FEM solver. So like on the GitHub, I have two different versions. Actually, I have three different versions. So one of them is MATLAB version, which is the most efficient one, the fastest one. You can just download the entire folder and run the example cases. But if you don't have a powerful computer, you can use Google Colab, and then you can run the same code in MATLAB. I'm sorry, in Python. So again, like the name of this repository is like waveguide underscore FEM underscore solver. And here you see like the files. So this is a full vectorial finite element based solver for dielectric waveguides. So the question is, like basic question is, how electromagnetic waves are confined and propagate inside these almost lossless materials such as silicon nitride. I wrote the formulation and I uploaded my formulation with some example cases on archive. So if you go to archive 2604.12.01.14, you can also see the formulation, but actually you don't have to, so it's just for your information. So this is a typical output of MATLAB, and this is a typical output of Python. Like it shows us the X, Y, and Z components of the electric field densities. At the top it says that this is the resonant mode number 1. Effective index is 1.812 plus some imaginary portion. So imaginary part means there's small loss. So like both solvers in either MATLAB version or Python version, they have their own built-in mesh generator. Very simple mesh generator because the structure is like very simple. I will show you. And right now in our library we have three materials only: silicon dioxide, silicon nitride, and lithium niobate. But for this project, we will only pay attention to silicon nitride core and silicon dioxide cladding. One of the outputs is the TE-TM fraction. So it will actually output the TE fraction. So if, let's say, TE fraction is like 99%, it means that this is mostly a transverse electric. If it is a very small number, let's say 0.04%, it means that it is mostly a TM, the transverse magnetic mode. But like unlike waveguides surrounded by metal walls, here we are working with dielectric waveguides, and in dielectric waveguides we don't have 100% TE or 100% TM mode. So always we have hybrid modes. So again, you can go to the paper and you can learn how the algorithm is working. And in this project, we are only interested in effective index. I should say, like mostly interested in effective index. So effective index tell us how fast or how slow the phase of the electromagnetic wave changes inside this bus waveguide. So this is a typical structure. Like you can have a dielectric core on top of a box surrounded by a cladding. Like when I say box, it's like substrate. But again, for this project, we will only have silicon nitride core and silicon dioxide surrounding. Okay. For the core, we will define the core width and core height, but we also need to define the computation domain dimensions. Okay. You can, if you have a powerful machine, you can use your local machine. You can download my Python codes. But today I want to show you how we can use Google Colab and do the simulation. So let me change the. So this is a simple example as I wrote here. The first thing you should do is like, so again, this is the Google Colab. If you go to colab.research.google.com, if you have a Gmail account, then you will have free access. Actually, let me first show you that one. Like Colab. So I'm going to, like, this is the address of Google Colab. When you enter, you see something like this. On the left bottom, there's an option called like a blue region, new notebook. When you click that, it will create you a simple empty notebook. Okay. Oh, what's going on? Oh, how great. Okay. Okay, now let's go to the notebook. Again, this notebook also can be downloaded from my GitHub repository. Okay. All right. So the first thing is like pip install waveguide / FEM version 1.12. Okay. Then we upload bunch of modules from my solver and also from Python, such as like NumPy, matplotlib. So like you just need to press enter, run anyway. So right now it is going to install the waveguide FEM. It says successfully installed. Good. Then we will load important lots of modules. Good. Now we are going to define our parameters. So in this solver, all the dimensions are given in micrometer. So when you say wavelength is equal to 1.55, it means the wavelength of the laser is 1.55 micrometer. So here geometry parameters like width of the core is 1.6 micron, height of the core is 0.7 micron, the thickness of the cladding is 2.7 micron, and so this is like when we say cladding, so that's the part like the thickness for, I should say, maybe z greater than equal to 0. And when we say h box is 2 micron, it means that the length of the height of the region under the core is 2 micron, and simulation width, the computation width is 6 micron. Okay. Like these are all dispersive materials. That's why we have to use their correct refractive index. For example, in the second following line, I say like the core of refractive index of the core can be calculated from our modules get refractive index. Here we say the material type, silicon nitride, and we just here mention the wavelength. Okay, so it's like 1.55. So we get the core refractive index, we get the cladding refractive index, and then since like here there won't be a third material, I just set the refractive index of a substrate to be same as the cladding refractive index. So next I enter the number of modes that I'm interested in. So I set 6. Okay. For mesh resolution, so this means like how finely we create those triangles. I choose wave simulation width divided by wavelength. For example, here simulation width is 6 micron, the wavelength is like 1.55 micron. So basically it is like 4 lambda, and we multiply this number with 80. So it says, you know, mesh resolution is like 320. So it is like very high number. So it will create a very nice mesh. Then we print the refractive index of the core and cladding. Then we create the mesh. Okay, so like that, those rectangles will be divided into several small triangles, and like these are the nodes of the triangles, elements, relative permittivity, and the regions. So that is the way I created that mesh generator. Again, it prints the number of nodes and number of elements, and then it starts to record the time. Okay, so this is just for time keeping. Then we call the mode solver, compute modes. So we provide information, nodes, elements, relative permittivity, wavelength. Number of modes is like 6, and relative permittivity you can just set it to 1 because these are all non-magnetic materials. Once the solution is completed, it says that it took this many seconds, and then it will print the modes, mode number, effective index, and TE fraction. Okay, and then we plot the first 3 modes. Okay, so let me run this code, run this one. Now we will wait a bit. So it says the core refractive index is 1.996, cladding refractive index is 1.444. It created a mesh with 28,000 nodes, 55,000 elements. So like the nodes are the, just imagine, like think about a triangle, the corners are the nodes, and then we have edges, right? Okay, so it says assembling and solving the eigenvalue problem. All right. DOF is degrees of freedom. So right now we have 83,000 edges and 28,000 nodal, in total 100,000 degrees of freedom. It's a very, it's a large number. We don't have to use that high resolution, but in order to have very accurate results, the higher is the better. So it will take a while. Again, like this is quite slow. I mean, like Python version on Google Colab is quite slow, but the MATLAB version is much faster. And I love MATLAB more than Python. Sometimes my colleagues tell me that, oh, Ergun, like you don't speak English, you speak MATLAB. And I agree with them. I really love MATLAB so much. It's very efficient for me. Okay, this is taking for a very long time. I think it seems like we are running the code on Google Colab. If Google servers are busy, then it will take even longer. Maybe I should have chosen a coarser mesh. Okay, now results are coming. It says, look, here are the first 6 resonant modes. Effective indices. So for the first mode is 1.81. For the 6th one is 1.45. Again, imaginary parts are loss, very small amount, but we should keep an eye on them. And then here, so that is a TE mode, this is a TM mode, TE mode, TM mode. So normally you say, like, for example, TE 10, TM 10, TE 01, TM 01, and TE 11, TE 2, or so forth, so on. Like you can give numbers to those modes. And here, like you see the mode profiles, electric field XYZ component. You can save the figures, right? Yeah, so what do we need is as follows. Let me maybe create an Excel file. Do I have Excel here? Yeah. So what we will have is as follows. So let's say this is ring, not ring width, so waveguide, waveguide width, waveguide height, and then N1, N2, N3, N4, N5, N6, and then we will have so like waveguide. Okay, so this is for 1550. So for example, in this case, it was like 1.6. Waveguide height was about 7.7. And effective indices, I'm just going to copy from here. Oops, let me do this. Let me just go all the way down. So like we will have this table, which will have waveguide width, waveguide height, and the effective refractive indices at the let's say lambda. The wavelength is lambda is 1550, or I should say 1.55. Okay. Then we will change the wavelength. So I will give you the precise range of heights and widths and the wavelengths we are interested in. And in the end, we will have this large data set for to do like several things. One of the things I am interested in is is this kind of a structure. So I saw these structures being frequently used by the optics community. So there are two things we can do. One of them is using tidy 3D and simulating the structure in 3 dimensions. So we will have an input port, we will have an exit port, we will define some source, we will simulate it, and it will tell us what is exiting our structure. So tidy 3D has this website. Oh, not here. Let me go to home. Like there are a bunch of examples in there. For example, this one. Can I see it? Oh, this is just 2D. Okay, let's go back. Oh, what, this one? Oh yeah, this is 3D. See, like in this case, they have 2 waveguides, then they merge, then they split again. Here, so this is like input port probably, and then they have on the other side they have the exit port. So like we can look at these examples later and see how we can simulate the structure that I'm interested in, like something like this. So here, so my thinking is that we can numerically analyze this structure by using our 2D solver. And I have an idea about it because like this is like transmission lines in series, right? Transmission line 1, transmission line 2, transmission line 3, transmission line 4, etc., etc. And if my idea is correct, we can apply transmission line technique. I will explain that part like later, and we should be able to predict the output of this structure. And my prediction, and by the way, like people are using these structures for not only as filters but also as how do you call it, parametric oscillators. So that is next step. Another thing we can do again with this numeric with the data created with this study is inverse taper design. So inverse taper design, so like in optics, like we have these fiber optic cables. They are like micron. They are a few millimeters wide, right? But our frequency combs, they are extremely tiny. They are extremely small, like at the micrometer range. So what we have to do is we have to align our fiber and our frequency comb. But since there's a dimension mismatch, what we do is we use inverse tapered waveguides. And by using our data set, I'm positive that we can also come up with a very nice numerical method to design those tapers. So again, right now it's too early to talk about, but with this video, I just wanted to give you like a short introduction about how to use it. Once you are comfortable with it, then we can do other stuff. Thank you for watching this video.